Alright, so I wanted to make a little video here just to kind of fill in some gaps that I was forced to leave earlier today. And so I'm kind of just reading the notes with you here, but I want to make sure that we are on the same page about some of these things. So the first one is, of course, we have the definition of complex differentiable here, which means the limit of the difference quotient exists, right? Do more with that in a second. And then down here, Carthiadori's theorem. I want to look at the proof of that with you guys. So here it is. Theorem of Carthiadori, if you got a function with limit point A and f is complex differentiable at A, if and only if there exists a function phi which is continuous at A and satisfies this identity, which is to say that, f of z, notice that one of the things I keep using past this point is that this 2 is the same as saying f of z is equal to f of A plus phi of z times z minus A. Oh man, this green marker's toast. My son has colored with it too much. It's no longer capable of making fine print. Oh well, I tried. Anyway, so continuous, the function phi is continuous, and it is related to f in this way. F of z is equal to f of A plus phi of z times z minus A. All right, it's a different quotient function. So the proof that that's equivalent to complex differentiability is pretty straightforward, actually. Here it is. So suppose f, let me see if I can zoom in a little bit more. There we go. Here we go. So suppose f is differentiable at A, complex differentiable, right? Define phi of A to be f prime of A and set phi of z equal to the difference quotient, all right? Well, then we know differentiability of f means that the limit of the difference quotient is equal to the derivative, right? But since I set since I said phi of z is equal to this, right? That shows you that, and the value of phi at A is f prime of A. Well, this shows you that, in fact, phi so constructed is continuous, right? So therefore, f differentiable at A implies that 1 is true, that phi is continuous, and phi is actually also satisfying too, right? The equation, if this is the formula for z not equal to A, then you can solve that. That gives you that f of z minus, solve this, this gives you f of z minus f of A is equal to phi of z times z minus A. Just multiply this equation here by z minus A, you get that. And that's for a z not equal to 0, right? But, I mean, down here is the z not equal to 0 technically, right? But this is also true when z is equal to A, because this gives you 0, and this gives you 0. 0 equals 0 true, all right? So this identity, if this is the definition for z not equal to A, and phi of A is equal to f prime of A, then, excuse me, it follows that f of z is equal to, the identity, first of all, we have continuity, and second of all, we have this identity. Both of those come from assuming differentiability at A, all right? And then the reverse implication, of course, this is an if and only if criteria, all right? It's an equivalent characterization of complex differentiability. So conversely here, suppose that there exists a function which has properties 1 and 2, right? Now, the equation for 2, you can solve for phi of z, right? If we have the f of z minus f of A is phi of z times z minus A, then solving this for phi of z gives me phi of z is f of z minus f of A over z minus A, which I've written here. And that, of course, is for z not equal to A. So the limit as z goes to A of that is precisely the limit as z goes to A of phi of z. But remember, phi is given to be continuous in this converse direction. And so phi of z limit is phi of A. And then you can identify that phi of A has to be f prime of A. I mean, it is the value, the limit of the difference quotient is phi of a, so therefore phi of a is f prime of a by definition of complex differentiability. And so we've shown that the criteria of Carthiadori indeed imply complex differentiability at a point, and that's pretty neat. I went through this calculation with you guys in class, well, with the person who was in class, because, you know, as previously discussed individually, the arrangement. But let's see here. So this is the product rule. The quotient rule, I mean, look at with you. The quotient rule calculation here is really kind of sneaky. So here's how to derive the quotient rule by direct algebraic manipulation. So suppose f and g are complex differentiable with g of a not equal to 0. Define h to be the quotient f over g. Then that means hg is equal to f. And then, so we have h times g of z is equal to f of z. But remember, I'm using the Carthiadori formula to express g of z and f of z, right? Then I add 0 in a sneaky way by adding and subtracting h of a, right? And then I do some algebra here. So I have h of z minus h of a times the g formula, and then that's the plus h of z. Okay. Oh, I'm an idiot. So here it is. I was looking for this term. So I subtract that to the other side, right? Let me do some underlining here. So what's going on is I'm taking this term right here, and I'm subtracting it to the other side. Of course, it's this times the formula, the Carthiadori formula for g. And so when I subtract that to the other side, it gives me these terms over here, right? And then I'm still left with this stupid marker again. I'm still left with these two guys. Still stay there, right? So I've got h of z minus h of a times this is equal to f of a. That stuff's still there, right? And then minus this. And then I divide by the coefficient of h of z minus h of a, like so. All right. Remember, I'm trying to calculate the derivative of h, and so you're looking for what's the the Carthiadori function for h, if you will. And so we should see it from here somehow. And so to do that, I have to factor out the I said f of a is equal to h h of a g of a. Sorry, I'm an idiot. So I trade that for f of a g of a, and when I do that, this f of a cancels with that. I mean, so what's going on is there's a cancellation. This cancels with that, okay? And that leaves you with phi f times the g of a, which I think I've dropped my g of a somehow. Where did that? Oh no, it just leaves you phi f here, and then minus phi g h of a over here. So that h, I mean, there's still an h times phi g there, and remember h is f over g. So then you multiply the top and the bottom by g to get this. So when I multiply the h by g, it leaves me that f. So I get minus f phi g, and upstairs I get phi of f g divided by g of a squared, and then this term times phi of a. So this formula right here shows you that the h, I'll write it down here, h is equal to f over g, right? So the function f over g apparently has this guy right here as its Carthiadori function, all right? So this is phi h of z, right? Now the question is, so if that's phi h of z, then that satisfies the needed identity 2 for the Carthiadori criteria. And then the question is it continuous? Well, it is the quotient of functions which are, the numerator is continuous, the denominator is continuous, and the denominator is not 0 when we're looking at the limit point z equals to a, because g of a is assumed to be non-zero, and so when I plug in g equals to a, this is 0 plus something non-zero, so it's fine. The formula is fine at z equal to a. Therefore, this is a reasonable Carthiadori function, a different quotient function for this quotient function. This is a difference quotient function for this quotient function. That's a mouthful. And as such, well, this is what I'm saying in the next page, is that th is equal to this, right? And then that has the requisite properties. And also, when you calculate the limit, what does it work out to? It works out to f prime of a g of a minus f of a g prime of a divided by g of a squared. Our beloved quotient rule, right? F over g prime of a, right? And so what we have proved then are the usual laws of calculus, but now for complex derivatives, right? We did this one in class, the derivative of the sum of the derivatives, and I think I've left you this as a homework problem, all right, to prove this. So I want you to do a proof which uses the Carthiadori criteria. And you can basically just steal the proof, which is in my Calculus 1 notes, and just adapt it for complex notation if you want. It's really the same proof now. So then, let's look at these follows here. I want to look at right, so tell you what I'm going to do. I'm going to stop and take a different path for just a minute. And I'm going to do the example 2.24 in the standard way, okay? So here's the quote-unquote standard way, the usual. So this theorem of Carthiadori is not as well known as, of course, some other things I'm talking about. I don't think it's like a secret or anything. It's just like a lot of people don't think about this as much as I do. But here's example 1. If we have f of z equals to a constant, right, then what's f prime of z? Well, it's I guess I'll put an a here, all right? Then f prime of a, it's the limit as z goes to a, right, of f of z minus f of, so I'm writing down the template quotient here, yeah, right? What is that equal to? Well, that's the limit as z goes to a of c minus c over z minus a, all right? But that's the limit as z goes to a. Remember, in the limit, we're allowing z to get close to a but not equal to a. So this is non-zero in the limit, but inside the limit, of course. But c minus c is 0, so this is 0. This is 0, so there you have it. d dz of a constant is equal to 0, right? So of course, once you know that, then you can look at the case if I have d dz of a constant times f, right? Then by the product rule, that is what? dc dz f plus c df dz, right? But we just proved that dc the constant 0, right? So we get c times the f dz. So we can pull a constant out of the derivative. That's a consequence of example 1, the product rule, and example 2. Nothing here. I'm not doing anything about Carthiadori at the moment, am I? Okay, so example 3. Let's look at f of z equal to z squared. All right. Calculate f prime of a. So we're looking at the limit z goes to a of z squared minus a squared over z minus a. Hope you don't mind, I skipped the template step this time. I just went straight to the formula for f, right? And so of course we can factor. You've done this before. You just had x instead of z here, right? So you got z minus a, z plus a over z minus a. So these guys cancel, and that gives you 2a, right? So in other words, f prime of z is equal to, well, here we go, d dz of z squared. What is it equal to? It is equal to 2z. Still true in the complex case. What do you know? Now, let me just take a second here to contrast my, well, one more. I forgot my example 2.5. Right? F of z equals to z, right? Then f prime of a would be limit z goes to a of z minus a over z minus a, which is, yep, that's the limit of 1, which of course is 1, right? So d dz of z equals to 1. So not everything I'm telling you here, should be shocking. These are well-known facts from, this is equal to that, constant side of the derivative. The derivative of z with respect to z is 1. Hopefully that's not surprising. The derivative of z squared is 2z. Hopefully that's not surprising, right? And as you can see, the arguments I'm giving on this page are very much just the way we do it in Calculus 1, right? Here I'll do one more, like this. I'm gonna step it up a notch here. So suppose you're looking at f of z equals to z to the n, all right? Where n is an integer, positive number, okay? Then in this case, if we look at f of z minus f of a, right? So that's z to the n minus a to the n, right? Well then, that factors as z minus a well, I mean, fine. You know what? I mean, I could continue down this path, but I'm sorry. I need to take a step back here just for a second. So another way to characterize complex differentiability is this, right? F prime of z is the limit as h goes to 0 of f of z plus h minus f of z. You remember Calculus 1, we also had this choice. We could either take the limit as h goes to 0 or the limit as the variable goes to a in the usual notation. So it's more fun to look at this example 4 using this approach, all right? So what is f of z plus h here? Well, it's equal to z plus h to the n power. All right, and by the binomial theorem, that is z to the n plus n z to the n minus 1 h plus a bunch of uninteresting stuff plus n z to the h to the n minus 1 plus h to the n. So the specific coefficients here you can find in Pascal's triangle, all right? But the thing about Pascal's triangle, if you look at it, right, it has the binomial coefficients. And the ones that are next to the ones, so the outer coefficients, it's always just n. So like n equals to 2 has 2, 3 is 3, the 4 out here. So like this one, the next leading and the next to last, they're always, coefficients are n. That pattern continues. And so when we look at z plus h to the n minus z to the n all over h, right, and we take the limit of that, what happens? Well, we get the z to the n's cancel, right? And the h's reduce as well. So you get like limit as h goes to 0. Try not to write too much here. N z to the n minus 1, and then like the next coefficient, which I'm just gonna I forget the formula for it. I'll just call it n choose 2 is what it is. Anyway, so n choose 2, whatever that is, it's a number, not terribly important what it is, n minus 2, h. See, there was an h squared here, but the division by h canceled it. Like this h cancels with that h and gives me just the n z to the n minus 1 term. And then plus plus eventually I get to, n z h to the n minus 2 plus h to the n minus 1. Right? Excuse me. Anyway, the point is, here we're assuming n is greater than or equal to, I mean, you make it greater or equal to 2, I guess, if you want. But anyway, the point is, all of these guys, there's at least an h on them. And the limit of h goes to 0, this whole piece goes to 0. And you're just left with, of course, n z to the n minus 1. So the power rule, still true for complex variables. And if you look at my argument here, it is exactly the argument that we gave in Calculus 1. All right, so there's nothing... So what I'm trying to say is we could just recycle all of the arguments from Calculus 1 if we wanted to for the basic derivatives, right? Now what I have in the notes is a little bit different, right? Because I'm using the Carthiadori method for proving these things. So it looks a little bit different, but I wanted to show you what I just showed you, just to let you know that if these Carthiadori arguments leave you kind of confused, well, you can prove these things a different way if you want, like I was just showing you over there. Let's see here. So first of all, for like the constant function, then you can write it as the constant plus 0 times z minus a, and of course 0 is continuous function, and therefore it satisfies Carthiadori's criteria, since it's got the equation for criteria 2 and the continuity for equation 1. And the limit, of course, of that is 0, which means then the derivative of c is 0. For f of z equals to z, you have the identity f of z is equal to a, which is z, right? So z is equal to a plus z minus a, so I just add, subtract a, and notice that this time the difference quotient function is just 1. That's a continuous function, and it has limit 1, so therefore d dz is 1. Yeah. Z squared. For z squared, stupid cough. For z squared, you have f of z is z squared, and I added and subtracted a squared. So that gives me a squared plus z plus a times z minus a. So in this case, I'm identifying, so f a squared is f of a, so we've got f of z is equal to f of a plus z plus a times z minus a. That means that phi of z should be this z plus a term, which of course is continuous and has limit to a as z approaches a, and it follows from Carthiadori's criteria that d dz of z squared is 2z, because f prime of a is 2a from this, right? So anyway, there's another one. Oh, here, yeah. And if you're wondering where the a went, we had f prime of a is 2a, and so to rewrite that in d dz notation, that's d dz of z squared is 2z, right? It's just another way of expressing the mapping a goes to 2a. If we use the variable z, it's z goes to 2z. That's the derivative. Right, anyway. Here's the Carthiadori argument for z to the 4th. And so the Carthiadori arguments, though, I do admit they involve a certain amount of like sneakiness. And so here I added and subtracted 0. I added 0 again, and the reason I did that then is I can factor z minus a off z to the 4th minus a to the 4th, which gives me this. And so there you go, f of z is f of a plus this thing times z minus a, so this thing should be phi of z, which by the way is continuous and has limit 4a cubed as z goes to a. Hence, d dz of z to the 4th is 4z cubed. So, I mean, it is it is slick, these proofs of differentiability. And of course, well, I said you could find this polynomial right here using long division. I don't know if you know what I'm talking about or not, but like if you're trying to divide z minus a into, z to the fourth minus a to the fourth. So just so you know what I'm talking about, let me just review that right quick. So I do z cubed, so that gives me z cubed minus a z cubed, subtract, that gives me a z cubed, oh sorry, that's z to the fourth, my bad, minus a to the fourth, okay, great. And then I do, okay, so to get rid of that I need a plus az squared, so that, multiply that, I get my az cubed minus a squared z squared, subtract, I get a squared z squared minus a to the fourth, and then to get rid of a squared z squared, I do what? Man, I'm going to have to zoom out if I can see this. Then I do plus a squared z. When I multiply that by this, that gives me an a squared z squared minus a cubed z. Subtract a cubed z minus a to the fourth. So then I need a plus a cubed, right? And then I get a cubed z minus a to the fourth. Oh, goodness, good relief. The remainder is 0. It had better be because z minus a is a factor. And so this calculation motivates that we can factor z to the fourth minus a to the fourth as z minus a times that. Right, and that's what I wrote right here. Right about here. Come on. Whoa, whoa. Yep, yep, yep. See? There it is. Do. So, anyway. Let's see here, almost done. Then next I do the reciprocal function, and I do some kind of sneaky business. I say z times f of z is 1, so I add and subtract. So the game to play is to create a z minus a and a natural formula for the function, because then once you do that, then you can do algebra to find the quotient function. So, although I think I have a better calculation on the next page, this is kind of wacky what I'm doing. But so I have a f of z equals to that, and then I think next I divide by a. So like I divide this formula by a to get this formula, and that gives me f of z is equal to f of a plus f of z over a times z minus a. And so that indicates that the difference quotient function should be what? It should be, sorry, I'm trying to keep it in frame here. Difference quotient should be this piece, f of z over a, which is minus 1 over az. And that is continuous for a not equal to 0, and its limit is minus 1 over a squared. Therefore, you get d dz of 1 over z is minus 1 over z squared. Again, the same as calculus 1, right, but with complex. And I think maybe this is an even better way to do it. So just f of z minus f of a. In fact, you can just ignore, if you don't like the algebra we just did, ignore it. Just do this instead. F of z minus f of a is 1 over z minus 1 over a. Common denominator of that thing, you get a minus z over az, which is minus 1 over az times z minus a. So voila, there's your difference quotient function, phi. All right. And you can use the product rule to get the derivative of 1 over z squared, right, is minus 2 over z cubed. And for negative integers, you could do the quotient rule to get this derivative, right? So anyway, we have certainly proved the power law for integer powers. d dz of z to the n is n times z to the n minus 1. This turns out to still be true if n is a complex number, but in that case we have to think about the branch of the complex power function. All right, and as I told you guys in class, this is a tough one. See, because I don't know I don't know how to show the limit of z goes to 0 if phi of z is anything. I mean, if I could show its limit is 1, we'd be done, but that's not something we know yet. And anyway, so I think that is pretty much it. You know, we defined holomorphic at the start of class to be meaning it's complex differentiable at each point in the domain, which was a open connected set, right? And it's holomorphic at a point if there exists an open disk centered at the point. This example, f of z, this would have been good if I'd found time in class to do this one, but oh well. What this example shows you right here is if we look at the difference quotient for z bar, the conjugate of z, then it was z bar minus a bar over z minus a, right? And we need, for that limit to exist, right, for f prime of z to exist, we need the limit, f prime of a to exist, we would need the limit as z goes to a of z bar minus a bar, right, over z minus a. We would need that limit to exist. I would point out this is a two-dimensional limit, right? It's actually a limit in the plane. And for a limit in the plane to exist, for a limit of a function, two variables to exist, we need all the path limits to exist. So if you can find two different paths which give you different values, then it doesn't exist. And so like here, I'm looking at z equals a plus t. When I do that, this works out to 1. If on the other hand I set z equal to a plus it, right? So here's what's going on here. Here's the point A, right? So z equals to a plus t is a horizontal thing, right? Over here, z is equal to a plus t. Okay, here's the point A. So we show that if you evaluate the difference quotient on that purple line, you get 1. But on the other hand, if you evaluate the difference quotient on this vertical line, which has parameterization a plus it, right? When you evaluate on that red line, you get minus 1. So as t goes to 0, that gets you to the, what should get you to a. But we get minus 1 from one direction and 1 from another direction, and you can't have two different path limits. You can't have two path limits differing and have the two-dimensional limit exist. All right, so I'm going back to, I'm claiming some Calc 3 here. Actually, the limit we defined is very much the same as like a limit of a two-dimensional function we talked about in calculus. Calculus 3. I'll talk more about that in person, maybe Monday. But and then finally, this example here. We'll talk more about Monday as well. This gives you an example of a function which is just it's nowhere holomorphic, and yet it is complex differentiable on the coordinate axes. So anyway, that brings us to Cauchy-Riemann equations, where we'll start Monday. Sorry to go over time. Thanks, guys. Bye.